question is on finding the eigenvalues and eigenvectors of a given matrix. So before proceeding, let us look at the eigenvalue problem and see what eigenvalues and eigenvectors mean. So if we have a square matrix A and then we have a column vector X, then if this is equal to like this, where A is a square matrix, X is a column vector, and lambda is a scalar, then this is called an eigenvalue equation. This is eigenvalue equation, and over here X is called the eigen vector of A corresponding to the eigenvalue lambda. So a given matrix can have more than one eigenvalues. So an n cross n square matrix will have at least one distinct eigenvalue and at most n numerically distinct eigenvalues. So we can have different eigenvalues. So then we will have different eigenvalues and we will have eigenvectors corresponding to those eigenvalues. So here xi is the eigenvector corresponding to the eigenvalue lambda I. Now let us rewrite this equation slightly differently. So we have Ax equal to lambda x. So identity multiplied with any matrix leaves the matrix unchanged. So we can multiply it with identity over here like so. So then let us rearrange. This 0 is the column vector 0. So we get this equation. Now in order to solve this equation and to get non-zero x, so for non-zero eigenvectors cannot be 0. We want non-zero or non-trivial solutions. So for non-zero x, this given equation will have a solution only when determinant of A minus lambda I equal to 0. And why this is so, we can quickly check this. So if this is not the case, let us say if determinant is non-zero, then that means the matrix A minus lambda I is invertible. We saw in one of the previous videos on the inverse of a matrix that a matrix is invertible only when its determinant is non-zero. So if A minus lambda I determinant is non-zero, then that means A minus lambda I is invertible. So if it is invertible, its inverse will exist. So let us multiply the inverse of this matrix to this equation right here. So a matrix times its inverse gives us identity. So this is identity. So we get identity times x is a minus lambda I inverse times 0, and any matrix times a 0 matrix or a 0 vector will give us 0. So, and anything times identity leaves that matrix or vector unchanged, so we get the following. So we get, if this determinant of a minus lambda is non-zero, then that gives us x equal to 0, that is 0 eigen vector. So we do not want this condition. So for x not equal to 0, for non-zero x, we need to have determinant of a lambda I equal to 0, so that the inverse of a minus lambda I does not exist. Now this will give us a polynomial in lambda, and solving this equation, this is known as the characteristic equation. And solution of this equation are the eigenvalues lambda. So in order to find out the eigenvalue, we need to write this characteristic equation determinant a minus lambda I equal to 0 and solve for lambda. So this is how we find the eigenvalue. And once we get the eigenvalue, let us say we find one particular eigenvalue from here, let's say lambda I. Then we will go back to this equation right here and substitute in lambda I. So then when we solve this system of equation, this gives us the eigenvector xi corresponding to lambda I. So this is how we find eigenvalues and eigenvectors. Now let us look at the question. The question says, find the eigenvalues and eigenvectors of the matrix A, where A is given as follows. So this is our matrix and we are supposed to find the eigenvalues of this matrix. So let us solve the question. We need to write down the characteristic equation. So the characteristic equation is given as follows, and for our case a minus lambda I would be as such. So this determinant needs to be equal to 0. So let us write the determinant. sorry. So the solution to this characteristic equation are as follows. We have lambda 1 equal to 2, lambda 2 equal to 1, and lambda 3 equal to minus 1. We have these three different eigenvalues, and we need to find out the eigenvector corresponding to each of these eigenvalues. So these are the eigenvalues. Now let us look at the eigenvectors. So for lambda 1 equal to 2, let us start with the first eigenvalue. So x1, let us say, has the components x1, y1, z1. So this is a system of equations, and we need to solve for x1, y1 and z1 from this system of equations. So let us write it in the augmented matrix form. Wherein we will write the square matrix and the constant right hand side column matrix, which is 0 0 0 over here, and we will not write the variable matrix. We need to solve for the variable matrix by using row operations. So first row operation that we'll apply is R1 being interchanged with R3. This is the first operation. Then we will say we will use this operation. Next, we will use R2 goes to minus 1 by 3 R2, and finally we will use R1 goes to R1 plus 2 times R2. This is row operations used to row reduce the given system. So this is the reduced row echelon form. For the given system of equations that we started off with over here. So from this we will come to know the solution. So our first equation is y1 equal to 0 and z1 equal to 0 from these two equations, and we can set the value of x1 to be anything. So for normalized vector we will take x1 equal to 1. So this gives us the eigenvector as follows for the first eigenvalue. Now similarly we will proceed for the other eigenvalues. So the other eigenvalues were 1 and -1. So we have so for x2 we will keep x2, y2, z2 as the components. Again we will write it in the augmented matrix form. Now we will again apply row operations. So first row operation that we do is as follows. Then so this is our reduced row echelon form. And the solution to this would be as follows. We have the first equation giving us x2 equal to 0, and then we have y2 minus z2 equal to 0, and we can choose any value for y2 and z2. For normalization we will take this to be 1 over square root 2. So our eigenvector is as follows. So this 1 over square root 2 is there to ensure that the eigenvector x2 is normalized. Similarly, we will find the eigenvector corresponding to the last eigenvalue. For x3 we will take the components x3, y3, z3, now again the augmented matrix form will be as follows. And we will again apply row operations to solve this system of equations. So first row operation is as follows. Then we'll operate on R3. So this is the reduced row echelon form. And solution to this would be as follows. And again we can set this to any constant value, and for normalization purpose we will set it to 1 over square root 2. So this gives us the third eigenvector as follows. So this 1 over square root 2 is to ensure that the eigenvector is normalized. So this solves the question, and let us finally write all the eigenvalues and the corresponding eigenvectors. So eigenvalues and the corresponding eigenvectors. So we have lambda 1 is equal to 2. Let me just check. Yeah, lambda 1 equal to 2, and this is x1. Then we have lambda 2 equal to 1. Lambda 2 equal to 1. And finally, for lambda 3 equal to minus 1, we have the eigenvector x3 as follows. So this solves the question where we were supposed to find the eigenvalues and the eigenvectors, and we have found the 3 eigenvalues and their corresponding eigenvectors for the 3 cross 3 given matrix. So this solves the question. In this question we learned how to find the eigenvalues and the eigenvectors of a given square matrix by solving the characteristic equation for the eigenvalues and then solving the system of equation for the eigenvalue equation to solve for the eigenvectors.